Hello everyone, welcome to the organic chemistry class. Today is the 7th session, and in the 7th session you're going to learn about introduction to organic chemistry reaction. Before we start, please remember to tap in on ACHIS, and also feel free to pause the recording and continue when you see fit. Okay, as mentioned, the topic for the session will be Introduction to Organic Chemistry Reactions. The learning objectives for the sessions will be: students are expected to be able to draw the mechanism of reaction using arrow, differentiate nucleophile and electrophile, and last but not least, differentiate different types of reactions. The references that can be read further from the session will be McMurray chapter 6 and Klein the first book chapter 8. There are 5 subtopics for the sessions. The first one will be tools for drawing reaction. Second, nucleophiles and electrophiles. Third, difference between base and nucleophiles. Fourth is types of reactions. And lastly, regiochemistry, Zaitsev and Hoffman products, as well as Markovnikov and anti-Markovnikov. So without further ado, let's start with our first subtopic, tools for drawing reaction. The mechanism of reactions show how the reaction occurred, and basically in principle it shows how the electrons move during a reaction. In a chemical reaction, it will always be in the form of an electron moving around the reaction itself. So for example, in this molecule here on the left, in the example, we have this molecule, and as you can see, there's an arrow which is going from this bond between carbon and chlorine, that the arrow goes to chlorine. This shows that the electron here in these bonds, so there are 2 bonds, remember, they are sharing electrons in the bond. It shows that the electrons here are moving towards chlorine. And as the result, it will be like this in the end. So this will be positive because this carbon is losing electron, and then there will be chlorine which has an 8 electron, and thus this chlorine will be negative. And because of that, this chlorine will be removed from the system, and then you will have this. So if you see an arrow with a sign, negative sign here in front of any molecule or any structure, that means the system in the reaction is using that molecule or that group. In this case, it's using a chloride group. Now because it's leaving, this carbon here becomes positive. So this is what we have, a positive carbon. And then another arrow with this without any negative sign. That means this is added as a reactant. So this will react to the molecule. In this case, the positively charged carbon. It is because oxygen has a 2 lone pair of electrons. And again, as you can see, the arrow goes from the electron towards the carbon here, which makes the new molecule looks like this. Now since this oxygen has 3 bonds, which is with 2 hydrogens and 1 carbon here, this oxygen is now positively charged, even though it doesn't deviate from octet rule, since it still has 8 electrons. So 1, 2, 3, 4, 5, 6, 7, 8. This is less stable, which then this oxygen is positively charged, and then the same thing will happen. The bond here, which shows a 2 electron or 1 pair of electron, is moving towards oxygen, and then the hydrogen is being attracted by another water molecule from the electrons, just like that. And then in the end you got this molecule, and this all of the atoms fulfill the octet rule. So what you might want to understand from this reaction is that arrow always go from electron towards something. It could be bond, it could be carbon, it could be an atom. Second, if you see a negative sign here above an arrow, that means it is losing a group. Third, again, if you see a molecule above an arrow, that means it's a reactant. Doesn't have to be a reactant, it could be a catalyst as well. So that's what you learn from this example. Arrows are described as tools, where the tail shows where the electrons are coming from and the head shows where the electrons are going. And remember, arrows show movement of electrons, never that of atoms. So even though if you see something like this, OH, and then it shows a movement like this, that means this is from the electrons from the oxygen, not the oxygen moving itself. Never that of atoms, always electrons, because you are not always have to draw the electrons. And the movement of electrons have to obey octet rule. So these are what you need to remember in chemical reactions, and basically you already mastered it. The diagrams of electrons. Electrons exist as lone pairs or as bonds. So there are two possibilities. Therefore, the possible movement of electrons are from a lone pair to a bond, from a bond to a lone pair, from a bond to another bond, and lastly from a lone pair to a lone pair, although this one could not be achieved in one step. Now let's see the example of them. Starting from a lone pair to a bond. So from the previous reaction that you observe, the tail is coming from a lone pair, as you can see here. So there's a lone pair in the oxygen, and this is the tail of the arrow. The head looks like going to an atom, indication of bond formation between oxygen and carbon. Okay? Oxygen and carbon. Thus it looks like this in the end. It's forming. So the arrow as if it's forming. See? This is the arrow. Okay. Alternative way, you could also draw dotted line to indicate the bond that is about to form. The head of arrow is going to the dotted line. So yeah, instead of drawing the arrow, you could form this dotted line between the carbon and the oxygen, and then the electron could be drawn as if it's moving towards the dotted line. As you can see here, the result will be the same as you can see here and here. Next, from a bond to a lone pair. Pair of electrons shared by atom in a bond, indicated by a tail. Here, this is the bond, the electrons shared in the bond, and this is the tail of the arrow. Move to atom to form a lone pair. So here, chloride has 6 electrons, or 3 pairs of lone pair electron, and then this bond here, the electrons move to the chloride, which resulted that from 3 lone pairs of electron, now it has 4 lone pairs of electron. Okay, as you can see here. From bond to bond. The electrons of the pi bond could attack a proton, or H+, and expelling chlorine in the process on the reaction that's happening here in the example. So here we have a double bond, which resulted that this double bond has one pair of electron, okay? Which means this pair of electron could attack this proton, okay, hydrogen. And then this electron here, again, one pair of electron moves to the chlorine. So it's expelling, and then it forms a new bond. Yeah, okay, so then it forms a bond with this carbon and the hydrogen here. Okay. So these are the types of movement between electrons. It is also possible to have more than one type of arrow in one type of mechanism. So you could have all of these 3 types, moving from one pair to a bond, moving from a bond to a lone pair, and from bond to bond in one reaction. Doesn't necessarily mean All of them could be there. It could be only one, it could be two, and it could be also all of them. So here's the example. So we have an elimination reaction, and this is the reaction. So the reaction goes that we have this molecule here, and then there's a base, and the base has a pair of electron, lone pair of electron, okay, lone pair, which then attacks a proton. Okay, so this is the first movement from a lone pair to a bond. Okay. And then this is a bond from carbon and hydrogen to another bond. So from this bond to this bond. Okay. And lastly, from a bond to a lone pair. From this bond to this. So there are three types in one of this reaction. Three types of arrow. But for now, you can ignore the product. All you need to do is the movement of the electrons. Now, directions of arrow. Which one makes sense? If you would like a practice, feel free to pause and then continue for the answer. Okay, so we have reaction number 1 and reaction number 2. Now let's see reaction number 2 first. The reactions here is between this molecule and hydroxide ion, which in this case the lone pair of electrons in the oxygen in the hydroxide ion is going to this carbon, and then the pair of electrons in this double bond is moving towards the oxygen. And then you have this as an intermediate. So electron first flow up, and then since this one is negative, it wants to be stable again by giving the electrons back to the carbon. And because of that, these electrons, the pair of electrons here, is going to the chlorine and then resulted in a new product. So reactions number 2 are okay. Now let's see reactions number 1. The reaction number 1, it's the same, but the movement is quite different, where it shows that first the electron here in the double bond moves to the oxygen, and then the pair of electron goes back to the double bond. Now in this case, this one doesn't make sense because the electrons are moving back and forth. Okay. So what? So all you so from this point you can tell, okay, this one is, this one doesn't make sense because why would this electron moves to the oxygen when then it's also moving to the bond, even though the product looks like it. So in this case, this one is not. Okay, so this one is not a good one. Arrows are always going in one direction at the same time. Okay, so you cannot go bond to lone pair together with lone pair to bond as shown in this one. So because this one is from bond to lone pair together with from lone pair to a bond. So you can only choose one at the same time. Of course, later on it could happen from lone pair to bond, but it happens in the second step. Okay, here is an example of bad arrows. If you would like to guess why is it called a bad arrow, feel free to pause the video and continue when you think you got the answer. So if you guess that this is a bad arrow because it looks curvy like this and not just like this or like that, then unfortunately you're not correct. The reason why this is a bad arrow because this is hydrogen, and you know hydrogen, if it fulfills the octet rule, it could only have 2 electrons. And that means the 2 electrons is already here, forming the bond between hydrogen and carbon. Which means if the arrow looks like this, that is as if electron is moving from here to there. Although in actuality, what's happening is that this lone pair of electron is the one attacking the hydrogen, which is this one. If you want to draw a movement of electron from hydrogen, you should use this. So from the bond where the electrons are to this position. Okay, so this is a bad arrow because it is a reverse arrow, that the electron doesn't move from, the arrow shows that the electron moves from hydrogen to this. Here's an exercise. Complete the mechanism of the following reaction by drawing the proper arrows in each step. Okay, now let's discuss the step. So in the first step, you have this molecule, okay, molecule number 1. And then you have hydrochloric acid. Hydrochloric acid is described as this. So what is happening here will be this double bond, which has a pair of electrons, will attack the proton. Okay, and the electron here will move to the chloride, which resulted in this intermediate. Okay, and because this carbon is losing the double bond, now this carbon becomes positive. So do not forget the positive sign. And this carbon got a new bond, which is this new hydrogen. Okay, hydrogen from the hydrochloric acid. And remember, since this hydrogen here is drawn by this double bond, now the chloride has 8 electrons, or 4 pairs of lone pair of electrons. Now, since this one is negative and this one is positive, this is what could happen. The lone pair of electrons in the chloride ion will attack the carbon where it is positive, thus forming a new bond. So this is the first step to form this, and then this is the second step to get this. The next part is drawing intermediates. In drawing intermediates, charge is conserved. As you can see here, this charge and this charge, these are called intermediates. The only change in formal charges comes on the first and last atom of the system where the electrons are flowing. If the overall charge is negative at the beginning of the reaction, then it must also be negative at the end of the reaction. So remember, intermediates in the intermediates you keep the charges, but that doesn't mean that in the beginning of the reaction you cannot have charges. You could have charges in the beginning of the reaction, and it still has to be conserved at the end of the reaction. So it doesn't change the formal charge. If the starter starts off with no charge, then it can split up into a positive charge and a negative charge. For example, here in the hydrochloric acid, it could be positive and negative. Now, as an exercise, draw the intermediate that you get after pushing the arrows. So here you have your molecule, and this doesn't have any charge, right, in the beginning. And there is one negative charge here from the hydroxide ion. So the arrow is already provided to you, which shows that the arrow goes from the double bond to the oxygen, and then there is the attack from the lone pair of electrons to this carbon. So what's happening is that there is this will become a single bond, and then there will be a new bond between this carbon and this hydroxide, which resulted in this product. Now actually, if you want to continue with the reaction, this is what will happen. Okay, so the lone pair of electrons from this will go back to the double bond, and then this carbon will have 10 electrons, which is not good because it doesn't fulfill the octet rule. So what would happen is that this will go to the chlorine, which then resulting in this product. Here, as you can see, the formal charge of -1 stays there. So from the beginning and the end, you have the same charges. Let's continue to the second subtopics, which is nucleophiles and electrophiles. Firstly, what is nucleophile and what is electrophile? Nucleophile originates from nucleo and phile, which means literally translated to loves nucleus. Nucleophile is a compound that uses its electron to attack another. Meanwhile, electrophile, electron and phile, which literally translated to loves electron, is a compound that attracts electrons or it is being attacked. You can also define it as nucleophile is a compound that originally is negative, and electrophile are compounds that are positive. Not all of them, but let's say majority. Here, where you can see that the curved arrow, remember, arrow always go from electron to something, okay? Its movement will always be from electron to something. As you can see here, this curved arrow shows that electrons moved from B negative to A positive. Thus, by definition, the B negative, where uses its electron to attack another, becomes a nucleophile. You can also get it here that nucleophile are always electron rich. And the A positive here is the electrophile. It's being attacked, thus it's the electrophile, and it is always electron poor. And then later on, the electrons then move from B negative to A positive and up here in this new covalent bond. So the electron is being shared. Example, which compound is the nucleophile and which compound is the electrophile in this case? You can guess it first. Okay, now let's go through it. By definition, nucleophile is a compound that uses its electron to attack another, which means this is the nucleophile because it's using the electron to attack the carbon. Okay, then that means this compound here is the electrophile. So that's how to determine which one is electrophile and which one is the nucleophile. Again, this is also electron rich, and yeah, you can assume that this is electron poor. Here are some molecules that are nucleophiles and electrophiles. So when you observe that it has a lone pair of electrons, then you can assume that it is nucleophiles. As you can see here, not all of them are negative. Okay, this water molecule has a site of a nucleophile, and also this amine has a nucleophilic site, which is from this lone pair of electrons, as well as this and this. Now the other two examples are very electron rich and they are very strong nucleophile. Some are electron poor. For example, here this oxygen is positively charged, and this is very poor in electron because it's all of it are occupied. It doesn't have a free space where electrons are there. And here in this methyl, this part here, this blue part, this one being shown in arrow, is also an electrophile. Even though this is not fully positive, this is kind of partially positive. Again, another example here, this carbon here is also kind of a weak electrophile. Now, even though it also has a small nucleophile site there, this part. Remember, this oxygen has two lone pair of electrons, which means this is also partially nucleophile. In using curved arrow in reaction, there are several rules. The first rule is electrons move from nucleophilic source. This you can also write it as nu with an electron sign, or nu electron sign and a negative sign, to an electrophilic sink. You can write it as E or E+. The nucleophilic source must have an electron pair available, usually either as a lone pair or in a multiple bond. For example, here, in a lone pair, in a lone pair, in a lone pair, and in a multiple bond, which means there is a lone pair here. A pair of electrons, not a lone pair, sorry. And again, the arrow goes from the electron to the electrophile. Okay, electron, electrophile, electron, electrophile, electron, electrophile, multiple bond, electrophile. The electrophilic zinc must be able to accept an electron pair, usually because it has either a positively charged atom, positively charged atom, or a positively polarized atom in a functional group. For example, this is a positively charged atom, and this is positively polarized atom. So this is partial, we call it partially positive. Also in this case, it is partially positive, and this is also partially positive. Why it is only called positively polarized atom? Because it still has a bond with the other group. The bond is not broken yet. So for example, here it still has a bond with the halogen. Also here it still has the bond with oxygen, and here it still also has a double bond with the oxygen. Even though later on the bond could be broken by the electron moving towards the other group. For example, this electron moves to the halogen, this to the oxygen, and this to become a single bond. And the difference with this is that this only has 3 arms, which means this carbon is already losing its 4th arm. That means there is no longer a bond. So this is already a charged atom. The second rule is that the nucleophile can be either negatively charged or neutral. If the nucleophile is negatively charged, the atom that donates an electron pair becomes neutral. For example, this is negatively charged, so this oxygen is negatively charged, and then it attacks the hydrogen or the proton. Then the electron goes to bromide, then this one becomes neutral. Because it's already fulfilled the octet rule by doing this, and it has 2 bonds, 2 arms. If the nucleophile is neutral, the atom that donates the electron acquires a positive charge. Here, an example. So this one is neutral, and this electron attacks the proton, which means this one is attracting the proton. Then this one becomes positively charged because this one loses a bond. If you ask what would happen if this hydrogen goes to this carbon instead of this, then what you will get is the same version, which just make it different in the way of your feeling. And then this carbon here will be the one that is positively charged. So it's same otherwise. The third rule is that the electrophile can be either positively charged or neutral. If the electrophile is already positively charged, the atom bearing that charge becomes neutral after accepting an electron pair. Here, for example, this hydronium ion is positively charged. So when it is attracted, so the electron attracts the hydrogen, thus causing it like this, then it becomes neutral. There's another example that if you have this, which goes this way, then this one is neutral, it becomes negatively charged. So from positively charged become neutral, from neutral becomes negatively charged. This is the same case here. So for example, if you go, let's say, have a bromine here, a bromine negative, which then goes this, then this one, remember, this one is positively charged and this one is electrophile. This one will become neutral, with this reaction. So what you will have is this. Now this one is neutral. So it's the same principle. In the fourth rule, the octet rule must be followed. That is, no second row atom can be left with 10 electrons, or 4 in the case for hydrogen. If an electron pair moves to an atom that already has an octet, or 2 for hydrogen, another electron pair must simultaneously move from that atom to maintain the octet. When 2 electrons move from the carbon-carbon bond, here in the example of ethylene, to the hydrogen atom of hydronium ion, here hydronium ion, for instance, 2 electrons must leave that hydrogen. Here it is attracted, and this hydrogen already has 2 electrons, which means this has to move together at the same time, simultaneously. This means that the hydrogen-oxygen bond must break and the electrons must stay with the oxygen, giving neutral water. So here is the explanation, illustration on the 4th rule. This is also a reason if you see the previous example where you have this double bond, okay, and then you have a hydronium ion, okay, sorry, not hydronium ion, but hydroxide ion. Okay, this will go here, and then because of this carbon will have 10 electrons, which means at the same time, simultaneously, this double bond will have to go to this position to make it possible for a bond to happen. Here's an example. We have this product. Now, as you can see, here is what's happening. This is a water molecule, and there is also a hydronium ion. So there is a hydronium ion as well as water molecule. In this case, this hydronium ion is already positively charged, meaning this one could not become a nucleophile. Thus, in this case, the water, this becomes the nucleophile. And again, the arrow always goes from this to the carbon. This originally happened that this double bond is attracting the positively charged hydronium ion. It's attracting this hydrogen, and simultaneously, because this hydrogen already has 2 electrons, the electron has to move to the oxygen, which resulted in water, okay, neutrally charged water. And this becomes positive, this carbon becomes positive because it loses this double bond. Now there's a chance for this electron to go here. Okay, so it also happens simultaneously, otherwise this carbon will have 10 electrons as well. So what you will have will be here. Of course, if you want to continue, that's also possible that this is as if you have oxygen, hydrogen, and hydrogen, which resulted this oxygen becomes positive charge. So what will happen later on is that there will be another water molecule, okay, which then attract this hydrogen, which later on, yeah, you will get OH here in this position. Okay, so you have a neutral charge here. Remember, the beginning and the end should have the same formal charges. Another exercise, please add curved arrows to the following polar reaction to show the flow of electrons. Please pause the recording and continue when you see fit. Okay, now let's discuss this exercise. Now, as you can see here, this carbon is already shown that it has a free electron pair, which means that this might be probably the nucleophile, because this one's already rich in electron, even though this side could also be nucleophile, but we will see about that later on. Okay, now in this case, the product is already provided to you that you have this. Okay, now there is an extra methyl attached to this carbon. Now that it means it's probably this carbon. So what is happening here actually is that this electron will be attracted to the bromide, which then makes this bromide, yeah, it originally has 3 lone pairs of electron. Now this carbon becomes somehow positive because the electron is attracted here. So what's happening is that it goes to this carbon. Yeah, again, because this one is a pair of electron, it goes to the carbon. That is as if it's forming a bond, which means if it's as it is, this carbon will have 10 electrons, which is not possible. Thus, it is simultaneously, at the same time it is attacking this carbon here, this bromine is leaving together with the electron from this position. So this is what you have in the end. Okay, so that's for nucleophiles and electrophiles. Let's continue with the difference between bases and nucleophiles. The difference between nucleophiles and bases can be seen from these two examples. So in organic chemistry, all nucleophiles are bases, but nucleophilicity and basicity can be seen from how these nucleophiles or these bases work as. So in this example, you have reaction number 1 and reaction number 2. In this case, as you can see, in reaction number 1, the hydroxide ion is attacking the hydrogen ion. In this case, this is called a base. So when the molecule is attacking a proton, then it is called a base. However, when the molecule is attacking something else other than a proton, as you can see here in reaction number 2, this is attacking the carbon, which is the result of the this electron pair is being attracted to the chlorine. Thus, this will attack the carbon, which is now becomes positive. Okay, so this is attacking this. This becomes a 10. This carbon has 10 electrons, which means now there should be a simultaneous electron moving to the chlorine. Now this carbon becomes positive, thus it is being attacked by the nucleophile. So in this case, this hydroxide is the base in reaction number 1, and in reaction number 2, this acts as a nucleophile. Okay, so that's the difference between base and nucleophiles in simple terms. So here's an exercise. Identify the role of hydroxide ion in each of reaction step. Please pause the recording and continue after you work on the exercise. So we have two reactions, so the first one and the second reaction. Both reacted on hydroxide. Now the question is, are the hydroxides bases or nucleophiles, or base and nucleophiles? Now, as mentioned in the previous example, this hydroxide in the first reaction is attacking the hydrogen, which means this is a base. The hydroxide ion acts as a base in the first reaction. In the second reaction, the hydroxide ion is attacking the carbon. Thus, in this case, this is a nucleophile. So that's how you determine whether a species is a base or a nucleophile. Continue to the next topic, which is types of reactions. In organic chemistry reactions, it is divided into two, based on the kinds and based on how the reaction works. Based on the kinds of the reactions, there are addition, elimination, substitution, and rearrangement reaction. Any other reaction name that you might have ever heard are in principle the same way. Either it's addition, elimination, substitution, or rearrangements. It is usually just named based on who first discovered the reaction. And based on how the reaction works, it is either a radical reaction or a polar type reaction. We're going to discuss them one by one. In the addition reactions, in principle, you have two reactants that add together to form a single product with no atoms left over. So all atoms are being used. So here is an example. So you have an ethylene, which is an alkene, and then you react it with a hydrogen and bromide or hydrobromic acid. So you are adding the hydrogen and the bromine to this molecule, regardless of where the product will be. As a product, you're going to get a bromoethane where the bromine is attached to this carbon and the hydrogen is attached to this carbon. So you got everything as the result. So you are adding hydrogen and bromine to the molecule. In the elimination, it is a reaction where a single reactant splits into two products, often with formation of small molecules such as water, or hydrobromic acid, or hydrohalide, HX. Doesn't have to be hydrobromic acid, could be anything. An example could be shown here in this reaction. So we have an ethanol, which is an alcohol. So you have CH3, CH2, and OH. So this is ethanol. It cannot happen without any help from the outside reagent, thus an acid catalyst was added. So in an elimination reaction, it splits into two products. So alcohol becomes an ethylene plus water. Okay. Third, substitution, where the two reactants exchange parts to give two new products. So it is switching. So in this case, an example is given. We have a methyl acetate, okay, and then we have water, which they are switching parts, and then you get an acetic acid and methanol. Okay, so what's switching here is the methyl ester part and the hydroxide part. So it's switching between this and this in the pink and the green ones. Okay, so it's called substitution reaction. Lastly, a rearrangement reaction where a single reactant undergoes a reorganization of bonds and atoms to yield an isomeric product. Remember what isomer is, yeah? I'm not going to repeat about isomer. So the example given here is that we have a dihydroxyacetone phosphate, okay, and we have the structure. Pay attention to the position of the oxygen and the hydroxide group. It undergoes a rearrangement reaction to become a glyceraldehyde 3-phosphate. So it starts from a ketone and then it becomes an aldehyde. As you can see here, if you observe the position of the oxygen and the hydroxide, they are switching. So this is the kind of rearrangements. Of course, it doesn't happen just like this. There are a mechanism behind it which is not written in this case. So those are the 4 kinds of reaction. So remember, there are 4. The first one that you have learned is that was shown to you is addition, and then elimination, and then substitution, and lastly rearrangements. Okay, so these are the kind of reactions in organic chemistry. Based on how the reaction works, how meaning the mechanism. So there are 2 types. The first one is a radical reaction, and the second one is polar reactions. Radical reactions shows that the processes involve symmetrical bond breaking and bond making. What does that mean? We're going to see later on. Meanwhile, in polar reaction, it is a process that involves unsymmetrical bond breaking and bond making. Again, we're going to see how it works in the next slides. How bonds break. Here there are 2 examples given to you. So not 2 examples actually, yeah. Reaction number 1 and reaction number 2. It could be a homolytic where a bond breaks in an electronically symmetrical way so that one electron remains with each product fragment. If you remember, I once mentioned that an arrow, when it shows a full arrowhead like this, that means a pair of electrons is moving. Okay, but however, electron could also move alone, and it is shown by half of the arrowhead. A single electron is moving. Now, as you can see here in reaction number 1, if you observe, the arrowhead is only half, which means only one electron instead of 2 moved to the specific species. In this case, one electron moved to A and one electron moved to B. As a result, you get A electron, B dot, B electron, which you can call this A radical and B radical. Here, as you see the word. This is the type of a symmetrical bond breaking, where one bonding electron stays with each product. So you got 2 radicals in this case. The second mechanism is heterolytic, where a bond breaks in an electronically unsymmetrical way, so that both bonding electrons remain with one product fragment, leaving the other with vacant orbital. As a result, actually you have seen this a lot of times in this session. In reaction number 2, there is a bond between A and B, and all of the electrons, both electrons, are being attracted to B. So now A is missing electron, thus you got it A+. Meanwhile, B becomes negative because it is overloaded with electron, and you know electron is negatively charged. Here in this case, you have an unsymmetrical bond breaking, where it is polar that one is positive and the other is negative, where two bonding electrons stay with one product. So how do you determine which way the electron is moving if you have number 2 here? So we have A, B, and how do we know that the electron moves to B and not to A? That will be depending on the electronegativity. So for example, as you have seen before, so you have hydrochloric acid, HCl. Since hydrogen is way less electronegative compared to chlorine, thus the electron will most likely move to chlorine. So that will be depending on the electronegativity, resulting H plus and Cl minus. So H plus is A plus and B minus is Cl minus. After the breaking, the bonds could also be reformed. So remember from before, reaction number 1 and reaction number 2, you have A radical, A dot, A electron, what you call it, and then B radical and also B dot, that you have a dot which shows an electron. Again, the reaction, you should show the reaction as it is. So they're meeting like somewhere in between. So you have A and B, so each has an electron. So again, arrow should be from electron to something, electron to bond in this case. So the electrons are combining together. Okay, so they are meeting in between A and B. So you can draw the arrow here and here, it's up to you. I mean, as long as it's in the middle, in between A and B. So one bonding electron is donated by each reactant. This reaction is happening in a radical reaction. Secondly, unsymmetrical bond making is just the reverse way, so you have a positive charge and negative charge. Thus, as how arrow moves in chemical reactions, negative is attracted to positive. So the electron will attack the positively charged species in this case. So here are the types of radical reactions. You could have a radical substitution reaction, where that you have a radical here. So you have, let's say, A radical, or just radical species in this case, a reactant radical. And then you have A and B. So what's going to happen here is that the electron will be attracted to either A or B, but just a single electron in this case. Thus the arrowhead is only one. So in this case, you're going to substitute. Just like the substitution reaction, you're substituting the species. In this case, you're substituting B with RAT, okay, with the radical. So you got a new product where it's a combination between A radical and the radical reactant, which is the substitution product. And then you still have a product radical, just like that. Okay, so it leaves as it is. You could also have a radical addition reaction, where you still have the same reactant radical shown here, and then you have an example given here is an alkane. So one of the electron here will be attracting this electron, thus causing a new bond to be formed. So here there are pink and blue. So one electron is blue and the other electron is pink. Let's use red. Okay. So as you can see here, the electrons are being shared between the electron from the radical species in red and electron from the double bond, which is in blue. While it should be 2 from the blue, thus the other unpaired electron will go to the other carbon, which is this unpaired electron. An example of a radical reaction can be seen here in the synthesis of prostaglandin. prostaglandin is a hormone which induces pain. So you have arachidonic acid and oxygen radical in this case. So this one single electron from the oxygen radical will be attracting this electron from this bond. So as you can see here, one of the electron from originating from this bond is moving to this one. Okay, see, there's only one arrow, half arrowhead here, also half arrowhead from the oxygen, and the other electron goes to this bond. So there will be a radical substitution where, yeah, you have a carbon radical in this arachidonic acid in this case, and then yeah, you have a Fe. Oh, and now the oxygen has full species, so it is ignored now. And then an oxygen radical that you might have from oxygen, okay, from oxygen here, that you have an oxygen radical will be taking this double bond, again the same one. So there are two electrons here, one electron is attracted to this and one electron moves there. Okay, so then a radical addition happen. So you are adding these two oxygen and oxygen to this arachidonic acid, a radical arachidonic acid, to form a new molecule called prostaglandin. So okay, so you have this carbon radical and so on, then in the end you have a prostaglandin. So you have both reactions, substitution and addition, in the synthesis of prostaglandin. Next is about polarity pattern in some common functional group. As mentioned before, the the mechanism of reaction work, which is based on the polarity, will look like this. So an example are given in this table. Alcohol has carbon and oxygen, where if you know from an electronegativity, carbon is less electronegative, while oxygen is more electronegative. Okay, oxygen versus carbon. In this case, alkene, it's the same, it's symmetrical, thus it's non-polar. In alkyl halide, as you know, electronegativity of a halide is more than carbon, so it looks like this. And you know, it's not split up, thus you still need to add this symbol, which yeah, the symbol it's called delta, or you can also call it partial. So when you observe something like this, alkyl halide, then X, if you observe this positive and negative, thus this means the electrons are attracted to that side. Okay, electrons are drawn towards the X part, thus you call this partial positive and this as partial negative. The bond is still there, it's not broken yet. It's very different when you have this. This is already positive, so you do not call this partial anymore. So this is already positive, and then you have this is also already negative. But in this case, in all of this table, you can see that depending on their electronegativity, the electrons will be attracted towards the atom which has a higher electronegativity. Okay. Thus, the partial positive and partial negative will be affected by this. In this slide, you will be shown the interaction of functional groups with acid or base. Here is a heat map, as you can see, a heat map where it shows a rich electron or a poor electron, where red means it is rich in electron. Okay. Now in this case, methanol, even though it's a weakly electron poor carbon, this hydroxide species is rich in electron. Okay, this oxygen. As you can see here, it has a 2 pair of electrons. Thus, it is also possible that this species, this oxygen species, is attracting proton. So if you add any kind of acid which donates proton, then this oxygen will most likely be attracted to the proton, which resulting from a electron-rich species, in this case, attracting the proton, will then end up as a strongly electron-poor carbon, because all of these species are already occupied. So yeah, now it's just poor in electron. So starting from weakly electron-poor carbon to become a strongly electron-poor carbon. So it could also be affected by acidity or basicity. So if you want to increase the strength of acidity or basicity, you could do something like this. In the way of polarizability, as the electric field around a given atom changes because of changing interactions with solvent or other polar molecules, as shown here, it could change, the electron distribution around that atom also changes. Larger atoms with more loosely held electrons are more polarizable, and smaller atoms with fewer tightly held electrons are less polarizable. So we already discussed this when we were discussing about how the size in an atom looks like. So if it is large, then the electrons are very far away from the nuclei, which means the bond between the nuclei and the electrons are in general weak. Thus, it's easier to polarize it. Okay, so it's the easiest to make it negatively charged. So for example, when you are comparing HBr and HCl, so hydrochloric acid and hydrobromic acid, since bromine is larger compared to chlorine, bromine will have a stronger polarity compared to this. Because if since chlorine is smaller like this, then the electron is even closer to the nuclei, thus the bond is stronger. Thus it is less polarizable in this case. Okay, so here is an example that you have carbon and sulfur and carbon and iodine. So carbon and sulfur are very close in periodic table, while carbon and iodine it's very far. Yeah, iodine is, if you remember, F chlorine, bromine, iodine. So this is at the bottom of period 7a, not period, group 7a. Thus this is very large, thus this is very polarizable. So this is very polar. So that's about the types of reactions and effect of electronegativity in reactions. Next, we're going to talk about radiochemistry, that in the kind of reaction, the reactions that you already discussed before, you could get Zaitsev and Hofmann products or Markovnikov and anti-Markovnikov products. So what is radiochemistry? Radiochemistry refers to where the reaction takes place. So as you have seen before in the previous example, you can see that the reaction undergoes in carbon number A or carbon number B and so on. That will be depending on the radiochemistry. So here in this example, so we have the same reaction. So we have this reactant 1 and 2, reaction number 1 and reaction number 2. There is called an elimination reaction. Okay, so this type of reaction is elimination. The question, where does the double bond will form? So in an elimination reaction, you either start with a single bond and then you ended up with a double bond, or you started with a double bond and you ended up with a triple bond. Okay, so that's an elimination reaction. So here in this case you have this position, so you have chlorine in this position, and then you have you add the base. So the base will take the hydrogen, and then this bond will move here, forming a new double bond. So you have this position. Okay, another example, it is also possible that the base will attract this hydrogen, and then the double bond will be formed here. So this is the same molecule, this and this. The only difference is that this one doesn't write the hydrogen. If you wish to do so, you can also write hydrogen here. It's the same. Also this one, hydrogen here. So from this single molecule alone, you could get both products. Either the double bond is forming here or the double bond is forming here. Okay, so that's possible. So here is what we call radiochemistry, where the reaction could the product could happen in this position, or it could also be in this position. Now of course, to be able to tell, then how do we call what this product is? We cannot say, okay, it is this product and this is this product. This should have a name. Thus the name was given already before. Now let's see what they are. So in here, double bonds can have anywhere from 1 to 4 groups attached to them. So if you have a mono-substituted, you get this. If you have a di-substituted, these are there. Tri-substituted here, tetra-substituted is there. Okay, yeah, mono, double, or di, tri, and tetra. Okay, so these are just a simple example. Now this regiochemistry is called Zaitsev and Hofmann product. Zaitsev and Hofmann are the name who discovered them, so you do not need to worry where this Zaitsev and Hofmann came from. Whenever we have an elimination reaction where more than one possible double bond can be formed, we have names for the different products based on which one is more substituted, which is called Zaitsev product, and which one is less substituted, which is called a Hofmann product. Now, what does a more substituted mean, or what does a less substituted mean? So let's go back to the previous slide. Let's remove the ink. We have the term substituted, right? Before, in the next slide. It is only a matter of whether it is more or less. Now, if you have a mono-substituted, that means this carbon here is more substituted compared to this carbon. This carbon is less substituted, okay? Because it has one substitution, meanwhile this one doesn't have any. In this case, both are the same because this carbon is mono-substituted and this carbon is also mono-substituted. So both positions are okay. Now, if we're comparing this and this, of course, the carbon on the left is more substituted and the carbon on the right is less substituted. While for this case it's the same regardless. Okay. So in this position, so we have chlorine, and then we're going to have a reaction. Now you know the double bond, if the base is attracting here, that means it goes here and then you have this position. Now, are these the more substituted carbon or the less substituted carbon? If our point of view is all of this position, 1 and 2, then this carbon, this has 2 substitutions. And in possibility number 2, we only have this. So we have 1 substitution here, and then we have 0. That means this one is more substituted, and this one is less substituted. Okay? Again, this has 2 substitutions on the left and on the right. Meanwhile, on the possibility number 2, we only have 1 substitution. Meanwhile, this one only has hydrogen. It doesn't have any substitution. Which means the possibility number 1 is more substituted and possibility number 2 is less substituted. And we call the more substituted as Zaitsev and the less substituted as Hofmann. Okay, Zaitsev product and Hofmann product. So that's what we call them. The next type of regiochemistry is Markovnikov and anti-Markovnikov. So we already talked about elimination reaction. Now, for addition reaction, we also have Markovnikov and anti-Markovnikov. It's the same principle. Markovnikov is when the substituted, the addition happens on the more substituted carbon, and anti-Markovnikov is when the addition happens on the less substituted carbon. So here we have possibility number 1 and possibility number 2 on the same molecule. Okay. So here in this case, the reactant is the same, hydrochloric acid and also hydrochloric acid, and then we have the same reagent. In this case, what could happen is that the electron will be attracting the proton, this one, and then it forms this, and then you have a positively charged carbon, okay, in this position. And because there's a positive charged carbon, the chlorine, which is now negative, will be going to this carbon. Okay, negative attracts to positive. Now in this case, the chlorine goes to this carbon. This is number 1. Possibility number 2, it's the same way that the hydrogen goes to this position, so it's still the same double bond, but now the carbon which takes the hydrogen is this carbon. Okay, so now the carbon which binds to hydrogen is this one, which makes this carbon to be positive now. That means the chlorine will be attracted to this carbon. Now you got this position. Okay, as you can see here, this carbon has 1, 2, and now 3 with the chlorine. While this carbon here now has 1, 2, 3, and 4 substitutions with the chlorine. That means in the possibility number 1, the chlorine is on the less substituted carbon because it only has 3 now with the chlorine, 3 subs. And this product is called anti-Markovnikov product or anti-Markovnikov addition. Meanwhile, for the second possibility, the chlorine is attached on the more substituted carbon, which is 4 substitution, and this is called the Markovnikov addition. So when the more substituted carbon is attached or is added with something, now you call it Markovnikov addition. This reaction doesn't normally happen, so when you need to choose which one, then should you choose? If there is no catalyst, for example hydrogen peroxide in this type of reaction in anti-Markovnikov, so in principle anti-Markovnikov reaction needs catalyst. If there is no catalyst, most likely the reaction will go to a Markovnikov addition. But you will still get this product regardless of whether you have a catalyst or not. If you have a catalyst, for example this hydrogen peroxide, anti-Markovnikov product will be major product, and Markovnikov will be minor. Major, minor meaning that let's say you have 100% product, and major will maybe you have like 90%, and then you have 10%. If you don't have catalyst, you will still get again both product, but in this case the Markovnikov will be the major and anti-Markovnikov will be the minor. Again, the ratio could be different, maybe this one is 95 and this one is 5. Regardless, you will still get both product. So that's the end for today's session. You already learned a lot, starting from number 1, how to draw an arrow, how to draw arrows in reaction. Number 2, you learn the difference between nucleophile and electrophile. Number 3, you also learn the difference between base versus nucleophiles. And also learn a lot of type of reaction. So you have based on the kinds, addition, elimination, substitution, and rearrangement. And also based on the mechanism, you learn about a polar reaction versus radical reaction. And lastly, you also learn about regiochemistry in organic chemistry reaction. So there are 2 which you have known, that it could be Zaitsev and Hofmann in elimination reaction. You also learn about Markovnikov and anti-Markovnikov in addition reaction.